So today I would like first to finish with a general discussion of the Noether theorem. And in this respect, I would like to consider an important topic, which is about conserved charges acting as symmetry generators. And then we come, as promised, to the case of a scalar field. We first discuss the classical theory of this field, and then we come to the issue of quantizing it. Before I continue with the new material, let me ask if you have some questions concerning what have been discussed in the previous lectures. It does not seem to be the case, so then let me continue. I will stop my video to have better connection. And the topic which I would like to briefly discuss with you is conserved charges as symmetry generators. So conserved charges that follow from Noether's theorem also play a role of infinitesimal generators of symmetries they correspond to. So conserved charges, let's write it this way, conserved charges which you find from the Noether theorem plays a role as infinitesimal symmetry generators. Symmetry generators means that they play a role of generators of a symmetry which they correspond to according to the Noether theorem. And to understand this statement, we need to recall the construction of the Hamiltonian formalism for the case of field theory. And normally we start from the Lagrangian description. So we have Lagrangian density, and the action. And to pass to the Hamiltonian formalism, we introduce, in addition to the canonical coordinates, which in this case is played by our fields, phi I x. This is our canonical coordinates. In addition to these canonical coordinates, we introduce canonical momenta, phi I depending on x, which by definition is a derivative of the Lagrangian or variational derivative of the Lagrangian with respect to velocity of our field. So as usual in classical mechanics, you know that momentum is a derivative of the Lagrangian with respect to velocity. And in this case, derivative with respect to velocity, you can also write as a derivative of the Lagrangian density with respect to T0 phi I on x, where I recall that d0 is a derivative with respect to x0, which is the same as speed of light multiplied by t. Now, this relation here between the momentum and the derivative of the Lagrangian density allows to express the velocity of the field in terms of or in favor of canonical momentum. And then we construct the Hamiltonian using the standard prescription of classical mechanics. We construct it as a integral of three-dimensional space. So we integrate over all, as an integral, yes, over three-dimensional space of the Hamiltonian density. And this Hamiltonian density is constructed according to classical mechanics in this way. So we have pi I dot minus Lagrangian. And this is, if you wish, the same as a dx and then pi I phi dot I minus Lagrangian density. Okay, and sometimes I will be writing this as an integral of a three-dimensional Hamiltonian density. So H here is Hamiltonian density. Hamiltonian density. I hope you are acquainted with the way we pass from Lagrangian to Hamiltonian in classical mechanics. And I'm implementing now absolutely the same procedure, but for the case of fields. Now, an important role in constructing the Hamiltonian formalism in the usual classical mechanics is played by an object which is called Poisson bracket. Poisson bracket, because this bracket allows to formulate Hamilton's equations of motion in a compact and a simple way. And in general, you know what is a Poisson bracket. So Poisson bracket is an operation on a space of functions on, say, phase space. So if you have a phase space, which is, say, parameterized by the coordinates P and Q, and then on this phase space, you have a space over this phase space, you have a space of functions, so functions depending on P and Q. And on a space of functions, you define an operation, which is called Poisson bracket, which is a map of functions, cross functions into functions. So any two functions on a phase space, it put in correspondence as another function on a phase space. And this Poisson bracket satisfies the following conditions. First of all, it is skew symmetric. So if you have two functions f and g, then the bracket is minus gf. Then it is bilinear. So f, say, lambda f plus mu g with h is lambda fh plus mu gh. And another important property is that it must satisfy Jacobi identity. So if you take a Poisson bracket of f and g, and then a bracket with enough function h, and then you add up as cyclic permutations of these functions f, g, and h, then the result must be equal to 0. So this is a general definition of the Poisson bracket. And for any, now we are dealing, since we are dealing with fields, now for any two local in time functionals, say f on p and phi, and the g on p and phi, so two functionals depending on momenta and coordinates. So in other words, so fields and their momenta, we define the Poisson bracket. Let's define the Poisson bracket as the following functional. The bracket of f and g is defined in the following way. Sum over all I, so over all species of fields, of integral over three-dimensional space, over all spatial directions of what? Of variational derivative of f with respect to pi I on x, variational derivative of g with respect to phi I on x, minus other way around, df over delta f over delta phi x, delta g over delta pi I on x. Okay, so that's a definition of the Poisson bracket, of the canonical Poisson bracket over the space of functionals, which now parameterized or depend on canonical coordinates and momenta. So you understand this replacement. So before we were dealing with functions on P and Q. So P and Q are coordinates, were coordinates on the classical phase space of classical mechanics. So to any point we put in correspondence a value, which is the value of the function on P and Q at this point. But now our space in the infinite dimensional case of fields, our space points in our space are functions. And functions on functions are functionals, if you wish. And on this space of functionals, we define a canonical Poisson bracket given now by this formula here. Now you can go on with this definition and compute the Poisson brackets between sort of coordinates on our infinite dimensional phase space, which are fields and their momenta. And a simple exercise to see that if you take two fields at different space points and at the same time, t, then the result of evaluation of the Poisson bracket between the fields is 0. No, that's simply because for this bracket to be non-zero, you have to vary one functional with respect to momenta and the other with respect to the coordinate. And here you have only coordinates, and therefore this bracket would vanish. The same is for momenta. So if you have a Poisson bracket of two momenta at different space points, then the result also will be 0. And finally, if you evaluate the bracket between momenta and coordinates at different space points and at the same time, then the result will be delta ij, delta function x minus y. So if you wish, this is a generalization of the standard or canonical generalization of the canonical Poisson bracket in classical mechanics to the case of fields. So fields themselves Poisson commute. Momenta of these fields also Poisson commute between themselves. And the bracket between momenta and its coordinate is proportional to the delta function delta x minus y. It is important also that in the Hamiltonian setting, the Poisson brackets are equal time. So what we are doing, we're computing equal time Poisson brackets. And as you see, the right-hand side of this expression does not depend on time. So Poisson structure, in a way, preserves in time. It's one and the same bracket for fields taken at the one and the same moment of time. That's why we are calling these Poisson brackets sometimes equal time Poisson brackets. Now, if we have the Poisson structure or Poisson bracket on our space of fields, then we can yeah.
Sorry to interrupt. What if it's for different time? Means if time is not equal, then
if its time is not equal, then you have to compute. You don't know what will be the outcome, and for that you need to solve equations of motion for the fields and then compute the Poisson bracket on the phase space in terms of well, we will see how we will do it. Eventually, we come to the point, what is the Poisson bracket between the fields, or commutator, if you wish, in quantum theory, between the fields at different moments of time. We will consider this. So what happens if t is not equal to t prime? We will see a little bit later. We will see a bit later. It's a good question. We will consider it. We come back to it. Thank you. I don't want now to run too far away, but I will come to this. This will be important question to consider. It will lead us to the notion of the Pauli-Jordan function. Meanwhile, if we have such a Poisson structure, equal time Poisson structure, we can define the time evolution of any functional, say f, under as people say, the Hamiltonian flow set up by your preferred choice of the Hamiltonian. So you pick up some function on a phase space which you would like to regard as the Hamiltonian, and then evolution of any function on a phase space can be described by means of the following formula. F dot, so time derivative of any functional under this Hamiltonian flow with Hamiltonian H, is given by the Poisson bracket of the Hamiltonian with F. And in fact, this is one of the standard equations of classical mechanics, and it goes without any modification to field theory. So if you would like to define evolution, time evolution of any functional, you compute the Poisson bracket, equal time Poisson bracket of H with F, and you get the time derivative. So it's like an equation of motion you set up for such, for any functional F in the theory.
Am I right that this is something related to some Liouville's equation, something like that?
Yes, it is related to the Liouville equation. Liouville equation play major role in statistical mechanics, because you write this Liouville equation typically for the density of states on the phase space. Here, the role, if you wish, this is very similar to the Liouville equation. The only difference, Liouville equation has a different sign. It has a minus sign on the right-hand side of the Poisson bracket, but yes, it can be interpreted under proper conditions as a Liouville equation in statistical mechanics. Then you should think about F to be a functional density, density of states on the phase space. Okay. This equation in classical mechanics with a standard Poisson bracket, by standard Poisson bracket or canonical Poisson bracket, I mean the bracket Qi, Qj is equal to 0, Pi, Pj is equal to 0, Pi, Qj is equal to delta Ij. Then if you take, say, coordinates Qi, then the evolution with the help of the Hamiltonian H and this Poisson structure will be the result of evaluation H with Qi, and you will find out that it is dH over dPi, right? And if you compute the time derivative of momentum, then according to this equation here, in the usual mechanics, you will find that this bracket of H with Pi will give for you minus dH over dQi. And this is nothing else as Hamilton's equations of motion, right? Hamilton's equations of motion. So what you see here, if you wish, are Hamilton's equations in field theory. You need to take this bracket here. You need to pick up a functional which you would like to regard as a Hamiltonian. And then for any functional f, its Hamilton's equations are given as a result of evaluating the Poisson bracket of H with F. Good. So this is, so to speak, the standard Hamiltonian formalism, which I would like to recall. And now we can look at the following question. So if you remember, the general expression for the Noether charge, which we got from the Noether theorem, is given by the following formula. So we take a zero, or if you wish, time component of the current, of the conserved current, and we integrate it over special directions. And this gives us the conserved Noether charge. Conserved Noether's charge according to the Noether theorem. And explicitly, we know what is this. So this is the following expression. So minus pj. And here we have this response function phi jn, depending on phi. In general, minus d mu phi I response x mu n, depending on phi, and then minus Lagrangian density x0 n, depending in general on phi, plus this boundary term, which is allowed by the Noether theorem, also depending on phi. And what I would like to do now, I would like to see what happens if I compute. So what will be the answer if I use my canonical Poisson structure on the space of fields for evaluating the bracket between the field and the conserved Noether charge. So conserved Noether charge, as you see, it's a functional on the phase space. So I've written it in terms of canonical coordinates and canonical momentum. So this expression Pj here is the derivative of the Lagrangian with respect to d0 phi j. You can look at the expression of the Noether charge we derived in the previous lecture or in the previous lectures, and see that what I'm writing here is this Lagrangian derivative, and this I replace now with Pj. And this we can easily compute. There's no problem to compute it because now we know this Poisson relations. We set up these Poisson relations, which we can use to explicitly compute this bracket. And let me just proceed and write what we will have. So what we will have integral with maybe one more property I forgot to mention about the Poisson bracket. Poisson bracket satisfies the Leibniz rule, and this is important. This is compatibility of operation of multiplication on a space of function with a bracket. So if I have two functions f and g and their product, and I evaluate the product of f and g with function h, then this is the same as f with h bracket multiplied by g plus bracket of g with h multiplied by f. Okay, so Leibniz rule. Leibniz rule, which is in a way shows you that the Poisson bracket acts as differentiation. So it satisfies the same property as derivative satisfies with respect to multiplication of two functions. What I mean is that if you have dx on f multiplied by g, then you have df over df over dx multiplied by g plus f dg multiplied by dx, and this is this property we called Leibniz rule in the usual differential calculus. And here something very similar happens for the bracket, right? If you have a product of f and g, then the bracket with any function h is you evaluate first f with h multiplied by g plus g with h multiplied by f. So bracket is supposed to satisfy Leibniz rule. And so now I just apply Leibniz rule and I write what I will get. So I will get the bracket of phi first with momentum. And since the bracket is skew symmetric, I can write it as in an opposite way. So pj on y, comma, phi I on x. And then I don't do anything with this term here. So I just rewrite it for the moment. Phi j n on phi minus d mu phi I x mu n on phi. Then I need not to do anything with pj on y. And I need to find the Poisson bracket, to take the Poisson bracket of this phi with this term here, right? But you see here, the non-trivial contribution comes only from this term here, and in particular, from the case when this index mu takes value 0. Because in this case, I get d0 phi, but d0 phi is d0 phi I is pi, right? For the case of a scalar field, this will be just the momentum. Yes, we will see it a little bit later. So let me just leave it as follows. So again, minus sign I will write, I will compensate by changing the order. And so the answer will be here that I'm taking phi I on x. No, minus sign, this minus here and that's minus here canceled. So I get phi I with d mu phi, let's write phi j. And then there will be x mu n depending on phi. Now, I don't need to take the bracket of phi with these response functions because I am assuming that response functions depend only on the field phi, but not on their time derivative. And therefore, according to this canonical Poisson structure here, the bracket of phi with phi is equal to 0. So I don't need to evaluate anything further. Here, in the remaining terms, I will not have any contribution from this term because it's only a function of phi, so there will be no contribution from this term. And concerning this one, here you have a Lagrangian, and Lagrangian might contain time derivatives. And so I have to take into account the bracket, the contribution of the bracket of my field phi on x with Lagrangian density, Lagrangian on y. And then x0n on phi left over. May I ask if it's clear what I have written down? I just use Leibniz rule to subsequently evaluate the possible non-zero brackets, the brackets which are expected to be possibly non-zero and to contribute to the right-hand side of this answer. Okay, so if this is understandable, what I will do next, I will compute the Poisson bracket of phi I on x with the Lagrangian density. And how I can do this? I know that Lagrangian density is a function of phi and the derivatives of phi. And therefore, I can, by Leibniz rule, differentiate Lagrangian with respect to phi, and then have a bracket of phi with phi, but this is 0. And so the only contribution, then non-trivial contribution, may come from the derivative, from the bracket of phi I with a derivative of, let's write here phi j like this. And here, in this case, we know that non-trivial contribution might come only if mu coincides with 0. And so I will get derivative of the Lagrangian with respect to d0 phi j on x, phi I on x, d0 phi j. And this is then I will leave no, maybe one more step. We know that what is written down here is pj, and this bracket will be non-trivial only if I is equal to j, I guess, because you see in this canonical structure which we have here, pi with phi j is non-trivial only if I is equal to j, otherwise it is 0. And so you
how
will get.
did you write this commutation relation in terms of partial derivative?
I mean the following. So L here is a function. So L is a Lagrangian density, and we know that this is a function of phi and the derivative of phi, right? This is Lagrangian density, so it's a function of these two variables. So in general, you have many fields. So you have fields phi j and derivatives of these fields. Then I suppose to apply Leibniz rule, right? And how you would do if you assume that if you know that the bracket acts on any function on a phase space in the same way as differentiation, how you would compute the Poisson bracket for the usual case of mechanics. Say, for instance, if you have qi and then a function of qi and qj and pj, what would you do by Leibniz rule? You would say that if the bracket acts as derivative, then you know the rule for derivative. If you have a derivative, say, of a function, of a composite function, say, function of, how can I explain this? What I would like to say is that by usual Leibniz rule, what you would need to do here is to differentiate f with respect to qj, and then take a bracket of qi with qj, plus derivative of f of with respect to pj, Poisson bracket of qi with pj. I mean, I would like to ask if this is understandable. This is in a way application of the Leibniz rule, and in a sense, this is in a way a derivative of a composite function, if you wish. So you first take your function and differentiate it with respect to qj, and then you need to find the derivative dqj over dqi. And here, in a sense, what you do, you are computing the derivative of dqj with respect to dqi. It's the same way as you would do differentiation of a composite function. By this, I mean that if you have function of g, f on g on x, what you would do, you say, I'm doing df over dg, dg over dx, right? This is how you would compute it. And since this Poisson bracket acts as a derivative in a sense of a Leibniz rule, that's what you do here. You differentiate the function with respect to its argument, and then you take a Poisson bracket of this variable qi with the argument of this function. And the same is here, since there is also dependence on pj, you differentiate function with respect to pj, and then you take a Poisson bracket of qi with the argument of this function. So this is a, if you wish, implementation of Leibniz rule.
So there is one differentiation with respect to del mu phi j, but what happens to del mu phi?
Yeah. So phi I already omitted because the bracket between phi I on x and phi j on y is 0. That's why I just omitted it. In principle, I have to write it, but since I know that this bracket is 0, I just omit it. Okay?
Okay.
So in principle, I should add to this, I should, strictly speaking, write here derivative of the Lagrangian with respect to phi j on y, derivative phi I on x with phi j on y. But then I know that this is 0, and that's why I'm not writing this term. Okay? And it's here, as the here is a similar story. So in principle here, you see I have a derivative with respect to mu. Here I have a derivative with respect to mu. But if mu is not coincident with 0, then I would have here contribution d, say, k phi j on x. And this is, derivative of phi y. So this is derivative with respect to y variable. And this derivative I can take out of the Poisson bracket because it's a derivative with respect to spatial direction. And it does not concern with the variable x because it's a derivative with respect to y. And then what I will get is the derivative dy acting on phi I on x, phi j on y. And I know that this is 0. And if I differentiate 0, I will get 0. That's why the values of this derivative with mu equals to 1, 2, 3, in other words, with the special directions, produce no contribution. But only contribution with d0 will enter because this is something which might be proportional to pj, because we know that this is what I'm doing here is phi j dot. But phi j dot, even in the usual classical mechanics, it would be qj dot. And qj dot, you know that this is momentum. If you consider the standard Hamiltonian, then standard Lagrangian with qj dot squared over 2, then canonical momentum will coincide with velocity, will be proportional to velocity, and that's why this bracket might be non-trivial. And therefore, I cannot ignore it. I cannot ignore it. I have to take this into account. Okay, so with these manipulations, what we are finding is that phi I on x with L on y, let me cleanly write what we get. We get here pj, derivative phi I on x d0 phi j on y. That is what we are getting from this exercise. And now I can just substitute this result back into the original expression here. And you see then what happens is that there is a cancellation between, nice cancellation between two terms. Let me mark them. This one cancels exactly with this term, because again, this will be non-trivial only if index mu is equal to 0, just according to the argument I gave. And this bracket we just computed, it is given by this formula, which is the same as this guy here. And so these two terms exactly canceled. And you are left with this expression here, but we know what is this. According to the canonical Poisson structure, I will get here delta Kronecker multiplied by delta function x minus y. So this is Kronecker delta ij multiplied by delta function x minus y. And therefore, I can integrate over y because of the delta function present. And I'm finding the following simple expression. Phi I on x with Poisson bracket of phi y on x with a conserved current, this Poisson bracket. equals to phi in response minus d mu phi I x mu n. And over mu here there is a summation. So this is only this term is left over upon integration over y. But what is this? This expression we have already seen in the lecture when we were constructing this conserved current Jn. What is written down here is nothing else as a variation of the form of the field phi I under the action of this conserved not a current. So variation of the form of the field phi I on x. So sometimes this variation of the form in classical differential geometry is called the Lie derivative. So Lie derivative. And what we are obtaining here is that now if I sum up this Poisson bracket, okay, if I sum this generators Jn with parameters epsilon n of my transformations, of my symmetry transformations, then here I will get phi in minus d mu phi I x mu n summed up over index n. And this is just a variation of the form of the field phi I under infinitesimal transformations with parameters epsilon. So that's exactly infinitesimal variation of the form we had in our Noether theorem. And this is exactly what I meant by a statement that infinitesimal variations of the form or infinitesimal symmetry transformations are generated by the conserved Noether charges with respect to the Poisson structure, to the canonical Poisson structure we have. Let me just give one concrete example, an important example, which is a demonstration of this property that conserved charges show themselves up as symmetry generators. Let's consider, for instance, time translation. We know that this symmetry corresponds to the conservation of energy. So time variable gets translated by adding to x0 infinitesimal parameter epsilon. And let's consider, for simplicity, just a single scalar field. Then we know that there is a conserved current corresponding to this symmetry, and this current is component of a stress energy tensor with indices T mu 0. This is component which is conserved, and this is local conservation of energy, if you wish. This is a law of local conservation of energy. Local conservation of energy. Now, the corresponding Noether charge.
Excuse me.
Mm-hmm. Yeah.
Here, conservation of energy means mc squared is conserved, right?
Sorry, conservation of energy means that the energy is conserved, and the energy is exactly what I'm writing now. This is a zero component of this current, right? That is a zero component. So mu is taking value 0, right? And this is T0, 0 component of the stress energy tensor. T0, 0 component of the stress energy tensor. And we take it and integrate over spatial directions. And then what we know about this J, so this is conserved Noether charge. So what we know is that if I will be differentiating it with respect to x0, so it means with respect to time, I will get 0. So this object is time independent. That's why it is conserved. And
but if I'm not wrong, it's a rho c square T00 component.
Sorry, say it again.
T00 component is a rho c square, right? If I'm not wrong.
C squared.
Rest mass energy density.
MC squared. No, because MC squared is the energy of a particle at rest. But in general, if you have a moving particle, this will not be the case, right? In relativistic theory, for a single particle, you know that it will be mc squared 1 minus v squared over c squared. That would be the energy. But what we are talking about here is not even particles, right? We are talking about fields.
Mm-hmm.
Yeah, so we are talking about fields. So in the case of a field, we have a concept of a stress energy tensor, which I discussed in the last lecture. So this was T mu nu. And remember, for this T mu nu, which expression, we derived an explicit expression. For the case of a single scalar field, we found that T mu nu is given by derivative of the Lagrangian with respect to d mu phi, multiplied with d nu phi minus delta mu nu multiplied by Lagrangian density. Remember, this is stress energy tensor for a single scalar field.
Yeah, got it.
Mm-hmm. Exactly. And now we are talking about 0, 0 component of it. So let's specify it. So I put here 0 and 0. I'll get d Lagrangian d0 phi, d0 phi minus delta 0, 0 is 1. So I get this expression here. Then you may do the following. You know that what you're dealing with here is momentum. So derivative of the Lagrangian with respect to Lagrangian density with respect to derivative of the field just gives you nothing else as momentum of this field, and then you get momentum multiplied by velocity minus Lagrangian. But according to what I told you about the Hamiltonian formalism, this expression is nothing else as a Hamiltonian density of this field. And therefore, this conserved Noether charge, J, in this case, is simply pi d0 phi minus Lagrangian density, the same as integral dx multiplied with Lagrangian density. And if you would like to have the proper normalization constants, you need to include 1 over c to be completely in agreement with dimensions. And then what I would like to write here, that this is nothing else as the Hamiltonian. So integral of the Lagrangian, of the Hamiltonian density multiplied by speed of light is the Hamiltonian. So Hamiltonian appears to coincide with a Noether charge corresponding to translations in time, to time translations. You see, so this means that in fact, the field phi on x under the action of this J, according to this formula here, must undergo the time translation. So our formula in this case will give the following. So in this case, what we know is that for a scalar field, the response phi capital on translations of coordinates and time is equal to 0, and this object here, x mu n, is proportional to delta mu 0. And therefore, here, what you will see is, according to that formula, the result will be minus d0 phi, minus d0 phi, where phi is our field. So phi is not, maybe I should be careful. I should be a bit careful in writing. It's not phi capital here. It's field phi itself. It's a phi on x. Yeah.
Yeah. For example, if you want to show that our momentum is also conserved, so we need to take other components of
absolutely,
momentum density.
absolutely, yes. The other components responsible for the conservation of the total momentum, they are related to dxt0i, where I will be running 1, 2, and 3. And this would be my next example to write for you. Exactly. So let me just finish with this. Now we know that J is 1 over C multiplied by the Hamiltonian, and therefore I can write it as 1 over C phi on x with the Hamiltonian. H is minus d0, and d0 is 1 over C d over dt phi on x, so C cancels out. This is I interchange by using the skew symmetry of the Poisson bracket, and in this case I arrive to the following equation. The Poisson bracket of the Hamiltonian with the field phi on x is equal to phi dot on x. And if you wish, that's exactly a manifestation of this Hamilton's equations of motion, which I declared at the beginning of today's lecture. We just see that the infinitesimal generator of time translations, according to this formalism, is nothing else at the Hamiltonian for our scalar field. The Hamiltonian generates time translation. And on the other hand, translation in time is a symmetry such that the corresponding conserved Noether charge, according to the Noether theorem, coincides with the Hamiltonian. And the Hamiltonian generates these symmetry transformations. It generates infinitesimal translations in time. I hope you get an idea. I hope you get an idea.
Excuse me again, a question.
No problem. Yeah, please go ahead.
Hamiltonian is a conserved charge with respect to the symmetry of translation in time. That means if this symmetry exists, the Hamiltonian is conserved. But we can consider the Poisson bracket between Hamiltonian and itself, and it's always equals to 0. So the derivative of this is
yes, you're completely right, because if I consider the Hamiltonian itself as a dynamical variable, so you compute the bracket of H with H to find what is H dot, you know that since the bracket is skew symmetric, then this is the same as minus H with H, because the bracket is skew symmetric under interchange. But since now this object, this function is equal to itself with the minus sign, it must be equal to 0, right? And so from here, you verified once again the conservation equation, H dot is 0.
But now I didn't see any symmetry. There is just a Poisson bracket without other conditions, I guess.
No, H is not transforming under this symmetry. H is invariant of this symmetry. But phi is not. The field is not. Field is transforming. Field is not invariant. The Hamiltonian is invariant. Field is not. Field is transforming.
Yeah, it is. I mean, now we don't know if this Hamiltonian is. I don't know. this system is invariant under time variation, under the translation in time.
But you see, this is something which you assume in the Noether theorem. Noether theorem starts from assumption that the action is invariant up to the boundary term under certain symmetry transformations, right?
Yes.
So you assume this. This is assumed it's an assumption of the Noether theorem. Now, suppose you assume that your theory is invariant with respect to time translations.
Yes.
Then if this is the case, you derive from Noether theorem an expression for the corresponding conserved quantity. And you know that this is integral of the component T0, 0. And then for the case of a scalar field, you see that the corresponding Noether generator, according to the Hamiltonian formalism, coincides with the Hamiltonian.
Yes.
But you made an assumption in the Noether theorem of invariance with respect to time translations. If you assume that time translations constitute a symmetry, then as a consequence, you obtain the statements that Hamiltonian generates these symmetry transformations in a sense of this Poisson bracket here.
Right. I
And
see now.
itself it's an object which is integral of motion, so it is conserved.
Oh, okay. Thank you.
So this is an idea. Well, you can do it in more general setting without split into spatial components corresponding to momentum conservation and energy conservation. You can just construct the generator P mu, which is the generator of space-time shifts. So index mu running 1, 2, 3. And according to this discussion, you will find out that this will be a generator P rho d mu phi rho minus Lagrangian density delta 0 mu, so 0 component of the corresponding stress tensor. Moreover, you can ask the same question about rotations, space-time rotations. And the space-time rotations, we know they are generated by the components of the angular momentum, so m mu nu. And for that, you need to take an integral of a 0 component of this tensor, m0 mu nu. And where coordinates and momenta, you do a very similar computation. Please do it as an exercise. Maybe you should do it in the exercise class to derive an expression for m mu nu in terms of canonical variables, canonical coordinates and canonical momenta. And you find the following expression: field phi mu p nu minus phi nu p mu. And then there will be x nu pi rho d mu phi rho minus Lagrangian density delta 0 mu, and minus x mu e rho d nu phi rho minus Lagrangian delta 0 nu. This is what you will find as an expression for generators of Poincaré group. So these are generators of Poincaré group. As functionals on a phase space. On the phase space. And phase space is, what is this? This is a phase space which is generated by fields where coordinates are fields and their momenta, of phi mu p mu. And even more to that, since now you understand these generators of Poincaré group as functionals, right? As functionals on the phase space, You can compute the Poisson brackets between them as between functionals on the phase space by using our fundamental Poisson brackets between the fields and momenta. So these objects here. Yes, this is what we can use now to compute the Poisson brackets between these Poincare generators, so generators of Poincare group. And so what you will find then with respect to this, so let me draw it in red just to stress. What you will find is that with respect to the Poisson brackets, these generators on the right-hand side reproduce the standard relations between the generators of the Poincare algebra. It will be eta nu sigma minus p nu, eta mu sigma multiplied by p nu, and the Poisson bracket between generators m mu m rho sigma will give eta nu rho m mu sigma minus eta mu rho m nu sigma minus eta nu sigma m mu rho plus eta mu sigma m nu rho. Great. That is what you will find. So in other words, the Poisson relations with respect to the Poisson bracket exactly reproduce you the standard relations between the generators of the Poincare group. But now considering these functionals, considering these generators as functionals on the phase space. This computation is a bit tedious, but it's nice to make it once to completely understand the concept of the phase space and the concept of these symmetry generators as functionals on this phase space. So once again, all what you need to do is these explicit expressions for Poincare generators as functionals of these fields and canonical momenta of these fields, use the fundamental Poisson relations between fields and momenta, and then you should obtain these relations here. Okay, any questions here? So in quantum theory, what happens is that these Poisson brackets will be replaced by commutators, and then you will get really the relations which represent the relations between Poincare generators as operators, and then this will be relations of the Lie algebra of the Poincare group. Now it's also relations between Lie algebra generators, or Lie algebra relations between the generators of the Poincare group, but now the role of the commutator is played by the Poisson bracket. And you know that one of the famous ideas of Dirac is that under the quantization, the Poisson bracket must be replaced by the commutator in the process of canonical quantization, and this is exactly what will happen here. Okay. If you don't have any questions, then I will consider the Klein-Gordon field. So I come to the next important topic, namely the so-called Klein-Gordon field, which is a scalar field. Klein-Gordon field. So the action for this field, which I continue to denote by phi on x, has the following form, which I will write with all the constants. So 1 over c 4-dimensional integral. Here 1/2 d mu phi on x, d mu phi on x, minus 1/2 mc over h bar squared phi squared on x. So Klein-Gordon field is a massive scalar relativistic massive relativistic scalar field. This term here is a term which contains kinetic energy. And this is, of course, something which we have already derived in the first lecture. So this term we derived from a discrete approach when we come from the model of our masses connected by springs. In the limiting case, when the number of masses tends to infinity and the distance, the lengths of springs tend to 0, we derived that in the continuum limit, the standard kinetic energy and the potential energy of strings gets into this expression here. And on the top of that, one may add something which is proportional to phi squared, multiply with the coefficient, which is designed in such a way that the physical dimension of this kinetic energy, kinetic term, and the term with phi squared is the same. For dimensional integration measure, d for x is understood as dx0, dx1, dx2, dx3, and the dx0 is c dt. So in fact, this speed of light here in front of the action stands to cancel this c, the speed of light, which is in dx0 element. The action is relativistic because here derivatives d mu are, you see, indices are paired in such a way that the corresponding term is invariant, will be invariant under Lorentz transformations. Field phi itself is a scalar, so we know how it transforms under coordinate transformations, transforms as is a scalar. From this action, we can straightforwardly derive equations of motion, and they have the following form: mc over h bar squared acting on phi on x. This is equal to 0. So this is these are Euler-Lagrange equation. This is Euler-Lagrange equation. Euler-Lagrange equation, which follows from this section. And if you wish, you can rewrite it more explicitly in the following way by just taking mu first to be 0, which will give you term 1 over c squared, second derivative in time. And then indices mu 1, 2, 3 will produce for you, according to Minkowski metric, the contribution d second derivative with respect to xi squared. And then there is a mass term mc over h bar squared acting on phi on x. And this equation here, it has a name of Klein-Gordon equation. Klein-Gordon equation. And sometimes it's also written in a way where this operator d mu is replaced by such an expression by box, where box is understood as this wave operator d mu. So by definition, this box is d mu wave operator. What else should be said here? In fact, this combination mc over h bar, if you write it in an inverted way, h bar divided by mc, this quantity has a dimension of length. lengths, because h bar, as you know, Planck constant has a dimension of angular momentum, so it's a momentum multiplied by length, and then you divide by mc, but mc has a dimension of momentum. And so momentum cancel, and you see that this quantity has a dimension of length. And this length is what is called Compton wavelength. Compton wave length associated with a particle of mass m. With a particle of mass m. So strictly speaking, what is standing here is not a mass, it's an inverse Compton wavelength standing there. But usually what people do, they prefer to work in the natural units where h bar is taken to be equal to speed of light is equal to 1. So h bar and c is equal to 1. This is what is called natural units. Natural units. In the natural units, then this term mc divided by h bar is simply becomes mass, and that's why with the convention that convention of natural units, the action for this field is written as the action for this field is written as S on the function on phi is integral d for x 1/2 d mu phi simply minus m squared phi squared, and people call this m mass of this field. Okay. What else should be said about it? We see also that if we return back to usual units, standard units, then we can write the action in the following form. So dt dx 1/2 c squared phi dot squared. Now I'm taking index so 1/c I restored in front of the action, so let me restore mc over h bar squared. And here d mu will produce for me 1/c dt, and twice gives me 1/2c squared phi dot squared minus 1/2 gradient of phi squared. This comes from spatial derivatives of phi, and then minus 1/2 is here, minus 1/2 mc over h bar squared phi squared. That's another way of writing the corresponding action. And now we can straightly develop the Hamiltonian formalism, and this is something we need for quantization. So we can derive canonical momentum for this field as taking the variational derivative of the Lagrangian with respect to phi dot on x. By the way, what is written down here is integral over time of Lagrangian. So Lagrangian is integral over dx of this expression here. And so you see that if I will be differentiating or taking a variation of the Lagrangian with respect to phi dot, I will find here phi dot divided by c squared. So this is how a canonical momentum looks like, or if you wish, I can write it also as 1/c d0 phi on x. This is the same expression here now. Derivative is taken with respect to d0. And if we use now the canonical procedure of passing from Lagrangian to the Hamiltonian, you obtain the Hamiltonian for this Klein-Gordon field, which is the following expression, integral 1/2 dx. And then you have here c squared p squared plus di phi plus mc over h bar squared phi squared. This is what you get by using this standard transition between the Lagrangian and the Hamiltonian. It's also interesting to know what is the physical dimension of the field phi. So dimension of phi I will denote as phi in the brackets, in the square brackets. So this will be physical notion for the physical dimension. And I use such a notation for dimension of any physical quantity. Just take it in square brackets, it will be physical dimension. And we know that a physical dimension of the Hamiltonian is, Hamiltonian has a dimension of energy. That's the same as energy. And what you see from here that energy, which is on the left-hand side of this expression here, should give us the following. On the right-hand side, you see three-dimensional integral, so there will be length cubed coming from the three integrations, dx. Then there will be, for instance, from this term, two derivatives, and derivative has dimension 1 over length, right? Because it's derivative d over dxi. So this has a dimension of 1 over length. And then there will be field phi coming twice, so phi squared. And so from here, you see that this is L phi squared, from where you conclude that the physical dimension of phi is a square root of energy divided by length. Energy divided by length. So this is a physical dimension of the field. Square root of energy divided by length. And energy divided by length is the same thing as energy per unit length. Per unit length. And such a quantity in classical physics, energy per unit length, is called tension. Tension. You might have in mind an analogy with a rubber band. So if you have a rubber band and you try to stretch it, then you inflect energy in this rubber band, and the more you stretch it, the more energy you put in it. And so energy divided by length is a tension, because this rubber band will produce a tension on your hands. And so energy per unit length in physics is called, that's the reason why energy per unit length in physics is called tension. So field phi has a physical dimension of a square root of tension. And momentum of this field, and we can also use the same procedure to find the physical dimension of the momentum. You see that, doing analogous computation, you will find that this will be 1 over CL square root of tension, like this. Or if you put everything under square root, energy C squared L cubed, like this. You can also rewrite this as energy has the same dimension as mass C squared, and in the denominator you have C squared L cubed, so C squared cancels. So if you wish, it's square root of mass divided by cubic length, length cube, and mass divided by volume, in fact. And the mass divided by volume, this is density, so it's a square root of a density, in a way. Well, you also can see now, if you return back to the action for this field, you can compute the physical dimension of the action. So let me quickly do it here. So physical dimension of the action, you get 1 over C. This is this 1 over C in front. Then you get 4 integration measures. dx0, dx1, dx2, dx3, which gives you L in the power 4. Then you have 1 divided by L squared from two derivatives, derivative 1, derivative 2. And then you have field phi twice. So it's dimension twice. And so you see from here L squared divided by C. And then phi squared gives you energy divided by length. And so you get length times energy divided by C. And length divided by C, so length divided by velocity gives you what? Length divided by velocity gives you time. And so what you get is time multiplied by energy. And time multiplied by energy is nothing else as angular momentum. Times multiplied by energy is the same as momentum multiplied by length is the same as momentum multiplied by length, and momentum is multiplied by length is the same as angular momentum, and this is has the same dimension as h bar, as we know, and that's why the action has a dimension of a Planck constant, and this is important to have in mind. So please remember, this is a very important fact, that the physical dimension of action is always the same as the dimension of the Planck constant. It always has a dimension h bar. It does not only concern a scalar field, it concerns any field. The dimension of an action is always the same as the dimension of angular momentum, and the dimension of angular momentum is the same as the dimension of a Planck constant. This is important to have in mind. So once again, just to conclude here, so dimension of h bar, if you wish, this is dimension of energy times time. This is the same as momentum multiplied by length. And this is by definition, momentum by length is the same as angular momentum. So if someone asks you what is the dimension of h bar, you can say it's dimension of angular momentum. It's the same as the dimension of the action in the action principle. Now, another important fact is the following: that if you have any two functionals of field momentum and the field itself, say phi and g, pi and phi, like this, then the equal time Poisson bracket given by the formula we discussed at the beginning of today's lecture, this dimension of this bracket, which I will denote as square bracket of f and g, this will be offset from the physical dimension of the product, so dimension of f multiplied by dimension of g, by 1 power of h bar, by h bar. So in other words, physical dimension of the Poisson bracket is not equal to the product of f with g, but it is offset by 1 power of h bar. And this you can easily understand, of course, from the definition of the Poisson bracket. You see that Poisson bracket is a differential operation, which explicitly given by the following formula. It's an integral dx, and then you have here delta phi over pi on x, delta g over delta phi on x, and minus delta f delta phi on x, delta g divided by delta pi on x, like this. And so we have computed that dimension of pi on x is, what was that? This was 1 over CL square root of energy divided by length. Dimension of phi we computed as square root divided by length. And therefore, here, in order to compute the dimension of the right-hand side here, physical dimension of the right-hand side, what you can do, you see that you have three integrations, so it will give you L cube, and then in the denominator you have pi and phi. So let's try first to see how it will work. So I will get 1 over CL square root energy divided by length, and then square root of energy divided by length. So it will give me L cubed divided by 1 over CL energy divided by L. This is probably not a good way I'm going to compute this. Maybe I will do it a bit different. I will do it, I think I know what I have to do. Let's do it in the following way. First of all, we need to find what is the dimension of this derivative. To be exact, we need to find what is the dimension of the variational derivative. And to do this, we need to consider what is the variation. So what is the variation delta f? So the variation delta f is an integral dx delta f over delta phi on x, like this, multiply with delta phi on x. This is what is called variation of functional f. And from here, you see that its dimension, which is the same as the dimension of f, of course, the same as dimension of f, is given by L cubed because of this integral here, dimension delta f over delta phi, and then by dimension of delta phi, which is the same as the dimension of phi. And so this means that I have here dimension delta f over delta phi multiplied by L cubed by square root energy divided by L. From where you see that physical dimension of this variational derivative, which features in this Poisson bracket, is given by dimension of f divided by which power of L? So this is L cubed, and then L minus 1/2. So 5 over 2, so length in the power 5 over 2 multiplied by square root of energy. So this would be a dimension of this guy. And so now we can compute the dimension of the Poisson bracket, f on g. We see that according to this definition here, we get L cube from integration. So L cubed, L cube. Then we get twice the dimension of this derivative. So we get dimension of f divided by L5 square root of energy, and another dimension of g divided by L5 over 2 square root of energy, which altogether gives me gives me what? And it gives me sorry, I do one mistake here. I need to find the dimension of derivative with respect to momentum. That is, I have not found. So I found the f over d phi, but I need also say the following thing: L cube delta g with respect to momentum, yeah, multiply by dimension of momentum, which gives L cube, and dimension of momentum, we know what is this. This is a square root of energy divided by c squared L cube, right? Multiply by dimension of derivative. So by this quantity here, delta G over delta T, and then this gives us then dimension of G multiplied by C, so this C here, divided by L in the power 3 over 2. This is 3 minus 3 over 2 here gives 3 over 2. And square root of energy. Yes, now we are ready. Now we are ready to compute the physical dimension of the Poisson bracket. So physical dimension of the Poisson bracket is the dimension of integration measure, L cube. Then comes the dimension of the first functional derivative with respect to phi, L in the power 5 over 2 energy in the power 1/2, and then dimension of the variational derivative with respect to momentum, which we find as G multiplied by C divided L in the power 3 over 2, half of the energy. And now let's see what we get. So we get here dimension of F multiplied by dimension of G multiplied by C. Here in the denominator, we get L in the power 8 over 2, so L in the power 4, and L cube in the numerator, so it will leave us L and then multiply by energy. And then you see that this is the same as F multiplied by G, and the speed of light gets down, so L over C multiplied by energy. And L over C has a dimension of time, so it's time. And energy multiplied by time is a Planck constant. And indeed, this is what I have declared. The dimension of the Poisson bracket of two functionals is not equal to the product of the dimensions of these functionals, physical dimensions of this function, but it's offset from them by 1 power of h bar, by 1 power of h bar. Any questions here? I think this is important to have in mind when we come to quantization. Now, the Klein-Gordon equation, which follows from our action, can be written then in the Hamiltonian form. The Hamiltonian I have already shown to you. The Poisson bracket is standard canonical, which I introduced at the beginning of the lecture, and for which we now compute the physical dimension. And the evolution of our field phi will be given by the Poisson bracket of this field with the Hamiltonian. And of course, the same will be for the momentum of this field. So this will be h with y on x. And these are Hamiltonian equations of motion. So from the explicit form of the Hamiltonian evaluating the bracket with phi, you will find out that phi dot will be equal to c squared multiplied by momentum. And from the second equation here, you will find that p dot will be equal to di squared phi. So sum of second derivatives of phi with respect to spatial directions minus a mass term mc over h bar squared multiplied by phi. And so these are nothing else as Hamilton's equations for the field phi. Hamilton's equations, which we can use to exclude momentum of our field by taking a second derivative, another derivative of phi with respect to time. So it will give c squared pi dot, and now instead of pi dot, we substitute this expression here. So we will get what we will get. We will get c squared di squared phi minus c squared multiplied with mc over h bar squared multiplied by phi. And if I divide now both sides by c squared and bring everything to the left-hand side, I will get 1 over c squared phi double dot minus di squared phi minus plus mc over h bar squared multiplied by phi equals to 0. And this is exactly our Klein-Gordon equation, which I started with. So d over dt squared minus d over dxi squared, if I write it in an explicit form, mc over h bar squared acting on phi is equal to 0. So these two Hamilton's equations here, they are equivalent to one Klein-Gordon equation. Klein-Gordon equation is reproduced. Okay. And the next important point to discuss is so-called mass shell condition. And in a way, this scalar field on the mass shell amounts just to solving the Klein-Gordon equation. So we have Klein-Gordon equation, and then now we want to solve it. Solve Klein-Gordon equation. How to do it? The most efficient way to look at the solutions and to understand how solutions look like is to go to the Fourier space. So what you just do, you make a Fourier transform by using the Fourier integral. So you write 1 over 2 pi in the power 3 over 2. This is conventional, but convenient convention to define the Fourier transform with such a prefactor. For integral, Fourier integral exponential I kx phi tilde on k, where phi tilde on k is a Fourier image. Fourier image of this field. Now this is this is integral over k. So I'm integrating over k Fourier image, and I get the original field phi on x. The product here, k multiplied by x, is a scalar invariant, Lorentz Poincare, Lorentz invariant scalar product, which is by definition k mu x mu, and this is the same as according to our notation for Minkowski metric, k0 x0 minus kx, where these are three-dimensional vectors of k and x. And very often, this is also written with the help of what is called wave vector. So k here is what is called wave vector, vector. And k0, I can also write as here ck0 multiplied by time minus kx. And this ck0 is what is called frequency. So this is omega t minus kx, where k0 then is omega divided by c. So the time component of this vector k is given by frequency divided by c. And this is, in fact, exponential I in the power omega t minus kx. In quantum mechanics, this combination is usually called plane wave. Plane wave. So Fourier transform for the field phi on x is, in fact, a decomposition over plane waves. If you wish, it's an integral over plane waves which is taken. And what you do next, you take this Fourier, this representation of field phi on x via Fourier image and plug it in this Klein-Gordon equation and see what you get for the corresponding Fourier image. Maybe one more thing is that very often people use in the books slightly different representation for the Fourier transform. Namely, they use the so-called energy type variables. Energy type variables. You may use it in especially it's very popular in quantum mechanics, where you use Einstein and the de Broglie formulas which relate energy and frequency and the momentum with a wave vector. It's like a transition between wave characteristics and the particle characteristics. And this is done with the help of this Einstein formula, where energy is h bar omega, right? The famous formula Einstein discovered by studying photo effect. And the second formula, which is due to de Broglie, is that momentum of a particle is related to the wave vector of the corresponding wave process, represented by this particle, if you wish, by the formula P is h bar multiplied by k. So Einstein, de Broglie formulas. So frequency then is energy divided by h bar. It's just like passing to a new variable with the dimension of energy. And here, instead of a wave vector, which dimension is 1 over length, one uses P divided by h bar. And so when replacing this omega t and k x by these new variables, then this I omega t minus kx goes into exponential I over h bar, energy multiplied by time minus p multiplied by x. Also plane wave, but now written by using energy type variables. And so in this case also, when you write now the field where it's Fourier transform, you have to make changes in the integration measure. So you will be integrating over variable E and over variable P, over momentum. And then because of this change of variables from K to energy and P, you will have here additional contribution of the type C. If I'm not mistaken, please check me, C h bar in the power 4, exponential I over h bar, et minus px multiplied by phi tilde on k. And the final thing is that you take one of these representations, for instance, this one, plug it into the Klein-Gordon equation, and you discover that Fourier image will satisfy or must satisfy the following equation. E over c squared. Here there will be phi tilde depending now on 4-component P. Minus P vector squared minus M squared C squared acting on phi tilde on P is equal to 0. Where P here, it has component, so it's a phi depending on p mu, where p mu, according to these definitions, is given by vector whose zero component is E divided by C, so that's P0, and momentum, three-dimensional momentum P. So here it's a square of the three-dimensional momentum P, and here you see P0 squared. And so this means that what you get is an equation of the following form: P mu, so relativistic square of P, minus m squared c squared, acting on a Fourier image of field phi, gives 0. So this is an equation which you have for the Fourier image. And here you might think that this equation is in a way trivial. It has only trivial solution. Phi tilde on P is equal to 0, because you might think that what you can do is just to cancel this prefactor, and then you get phi tilde on P is equal to 0. This would be so if you would deal with usual functions. But in fact, one of the important things which happen in quantum field theory and also in classical field theory here is that in general, you should not think about the field as about usual function on space-time. In fact, you should think about this field as being a distribution. So phi on X or phi on P, these are distributions on space-time. Distributions on space-time. And another way, another name for these distributions, generalized functions. Generalized functions. May I ask if you have any acquaintance or maybe a course on generalized functions or distributions, as we call them? An example, of course, a very characteristic example of a distribution is, for instance, Dirac delta function. This is an example of a function which is should not be understood as a usual function, but rather it's a distribution. And you know what distributions are. These are linear continuous functionals on a space of what is people call basic functions. In any case, if we understand the field phi in the distributional sense, then this equation here, P mu squared minus m squared c squared multiplied by phi tilde on P equals to 0, has the following solution. So phi tilde on P is given by a delta function on P squared minus m squared c squared, multiplied by some phi on P, which is a good continuous function without having any 0, where P squared minus m squared c squared is equal to 0. This is solution of this equation. Solution in the sense of generalized functions, sense of distributions. The condition P mu minus equals to m squared c squared is called mass shell condition. Mass shell condition, because it gives a relationship between the energy, between this variable E and the particle momentum. So this is this relation E squared equals to c squared p squared plus m squared c4. It is the same relation here, when this is equal to 0, then this is exactly the mass shell condition. And this is exactly what you learn in special relativity, a relation between energy and momentum of a single relativistic particle. Here, P vector, C squared, P vector squared, plus M squared C4, where this is something you asked me at the beginning of the lecture about M squared C squared. You see when P is equal to 0, then this goes into plus minus square root of M squared C4, which is the rest energy of a particle in the case of a positive sign, MC squared. Okay, so I think my time is up, so we will continue next Friday with the discussion of this Klein-Gordon field. I will finish the discussion of the solution, derive the on-shell form of the Hamiltonian for this field, and then I will quantize it. Okay, do you have any questions before we finish?
Professor?
Yeah.
For the solutions of Klein-Gordon equation, we considered the plane wave equation here. But
yes.
For example, if our space is not flat, it's not Minkowski, so will plane wave solution still hold there, or some modified version of it?
If our solution is not Minkowski, if our space is not Minkowski, no, then there will be different stories. Then there will be different story. Locally, it will be, but global properties will be changed.
So the wave solution should be different. So it's a modification.
In general, solution will be modified, yes. Because, I mean, in the general gravitational background, equation will be looking different. It will be invariant with respect to isometries of this gravitational background to which you couple your field. So this will change equations of motion, and correspondingly, it will change the form of the solution.
So we are studying this thing for the case of
Minkowski space. Yes, yeah. We are studying relativistic fields in Minkowski space. That's why for us Poincare group is so important, because Poincare group is an isometry group of Minkowski metric.
Yeah, understood.
Okay.
Thank you.
Other questions?
Yeah, I have a question about the convention, maybe. So in our lecture, we keep all the C and H bar put in some books, and maybe some other lecturers, they will just set those to be 1. So what would be the advantage of keeping all these parameters?
You mean well, you see, the point is that you can do all the calculations in the natural units. Then your formulas are simplified very much. Yes. You don't need to worry about this H bar C at various places. You throw them away. But eventually, when you get your final formula, which you want to check with experiment, like for instance, you obtain the formula, say, for cross-section of a certain process, you should be able, you need actually, you have to restore all the physical constants, like H bar, like C, to get a concrete prediction, say, for your cross-section. Right, you need to obtain it in physical units to know what you actually have to compare to experiment. So, from point of view of the theory, we can neglect all these dimensions and just work with natural units, derive our formulas in natural units, but then we should be able at the very end to restore on dimensional analysis. By using dimensional analysis on physical grounds, we should be able to restore all the physical units in the final formula. And I'm just explaining you how these things are working. I just want you to get some feeling about these dimensions. So you should be able, when it comes to necessity, to be able to restore these physical dimensions in the final formula. Okay? That's why I'm keeping them up to this moment.
Okay.
In many books, people just do it on the first page. You see, they say we work in natural units and we forget once forever about such things as H bar and so on. But then at the end, you have to, if you want to study various limits, you have to understand, for instance, a transition to classics, where is your H bar is sitting, which you want to send to zero and obtain, say, a comparison to the classical theory, how you distinguish it from interaction constants, what happens if you would like to go to non-relativistic limit, if you want to send c speed of light to infinity to discuss non-relativistic limit, you need to know where it sits, where this constant sits, right?
Yes, yes.
However, transition to non-relativism, transition to classics from quantum theory, then you need all these constants to be restored, and you need to understand how your physical quantity depends on them.
Yeah, right.
Yeah, but in principle, to simplify considerations, this approximation, you don't need to consider C, and this is indeed what people write for on-shell conditions, on-shell condition in many books. They put from the very beginning C and H bar to be equal to 1, and then mass shell conditions simply write as P mu is equal to m squared. Mass squared is equal to 4 momentum squared of a particle.
Yes, this looks much more easier.
Yeah, it looks simple and nice and very recognizable. Indeed, yeah, I have nothing against it. The only thing is that if you want now, for instance, to see how the action for relativistic particles goes to the standard action mv squared divided by 2, kinetic term of non-relativistic particle, or say energy of relativistic particle goes to energy of non-relativistic particle, you need to know where your speed of light is sitting to make it to infinity and to have this non-relativistic limit to be taken, right?
Yes, I understand.
Mm-hmm.
Thank you.
Okay, any other questions? Okay, if not, then I wish you a pleasant day, and we see and hear each other next Friday.